I thought that this would be useful for you all. I'm not going to go through it in detail because I can leave that up to you all. And it's really the same math we did last class. But if you remember, we were looking at that truss, 2 bars. And those 2 bars were really like linear springs. They're pinned together. They're pinned at some joint, and you just push on it. And the question was, what happens when you push on it? And what we did is we derived the total potential energy. I talked through that derivation here, so you can, if this was fast, you can kind of work through what I'm describing here. I discussed how we find equilibrium by setting the first derivative of this equal to 0, and then we got this messy nonlinear equation. I talked a little bit about some of the Mathematica syntax here, so if some of that's confusing, hopefully my comments have made it easier. And this governs equilibrium. So if you solve for your force, then you have an equation of force versus something. Often it's force versus displacement or force versus rotation, depending on your problem. In this case, it's force versus an angular rotation of that spring. And so then we plotted it and we got this really nonlinear response. I talked through how you should read this curve because I mean, when I first encountered this curve, I didn't really understand it at all. I didn't know how to interpret it. And so I talked through the idea that really what you're doing is you're starting here. That angle is pi over 3, which is the angle I chose for the arch. And you push on it, so you increase P. And you're following this curve. This is telling you what the angle is doing for given loads. And then what we did is we evaluated the stability of this forced rotation curve. And we did that by checking the second variation or second derivative of your total potential energy. So this is just 2 derivatives here. D. We use our solution for P because we found P. That was the force, the equilibrium solution up here. We insert that inside. And then our stability criteria is simplified to this kind of messy thing here. And we can plot this as well. And remember, equilibrium is defined when the first derivative of your total potential energy is equal to 0. Stability is defined when the second derivative of your total potential energy is positive. So all the angles on this graph that are above the x-axis are stable equilibria. And all the angles below the x-axis are unstable equilibria. It becomes a lot easier if you overlay these 2 graphs together. Blah. And you can see that the point at which this curve, the blue one, goes below 0, marks the critical point. This would be what would be referred to as the critical snapping load. If you go across here and identify what force this is occurring at, or this is the critical angle. You can't exceed that angle without snapping if you were to just look down. I went through some mathier things in terms of how do you find exactly where this point is, and that's up here. You can read through that on your own time if you're interested. I also went through the process of saying, well, how do you, if you know where this point is, how do you find this point? I did that up here so you can find the critical buckling loads. And so everything from inside of this vertical line to this vertical line are unstable equilibria. So this whole red curve here is not going to happen. You're never going to see it in practice. So what actually happens in practice is you load your curve, you start pushing your truss, pushing your truss, pushing your truss. You get to this point, you're applying a fixed amount of load. You should think of this as like you're hanging weights on this truss. So you're hanging some amount of mass on this truss. It gets to this point, it can no longer continue deforming because this is unstable to go to the left over here. But because you applied a fixed amount of force, it has to go find the next angle at that force that's stable. So I just walk across this horizontal line at this same force that I'm applying until I find the next part of the curve. And this part of the curve This angle is definitely stable. The blue curve is like way up towards infinity up there. So what happens is you push on your arch, it gets here, it becomes unstable, and it snaps, and it just kind of goes. You can unload it back, and it pops back up. That's how you should interpret this curve. And we found all of that by doing two things. Writing down the total potential energy, checking the first derivative to find equilibrium, and the second derivative to find stability. Are there any questions on this? Because what we're going to move to next is some of the advanced mathematics needed to do this for continuous structures. Right now, we just said there's just two springs, but it's not a beam. It's not a plate or a shell or a frame. And I'm going to talk to you about some of the challenges that comes when you move to more complex structures. But I don't want to do that until I get a sense that there's some comfort with understanding equilibrium and stability. So think of a question if you have one, and I'm going to switch gears to show you a homework assignment. If I can stop sharing here briefly. Oh, I'm not actually in this one. All right. So to get some practice with this, I cooked up a slightly different problem. The second homework, I had it on the syllabus as going out last week, but we're off by a little bit. That's okay. So this will be the second homework. It's just one problem. And it's 2 bars that are of length L. You can think of these as being rigid. They're not going to deform. They're not going to change length at all. The top and those black circles there are pins. So this thing is kind of simply supported at the at the edges. These 2 bars are pinned together. The top support is on a roller, so it can move up and down. Oh, I forgot to draw that. Hold on one second. Let me change this drawing very, very slightly. This spring here should also be on a roller. There we go. There's a spring holding these 2 bars down. That spring has a spring stiffness K. And what I'm asking you to do is you're going to need to write down the total potential energy. Again, I think this thing is going to buckle up into a triangle. So I think maybe something like your angle would be a good degree of freedom to be writing this down. So what's the angle that the beams make with the horizon? Or I guess in this case, the vertical axis. Write down the total potential energy. Find the force versus angle curve. See if you can graph it. Based on what you know differences between buckling and snapping, if you can identify what type of instability this is. Remember, buckling instability is what we found where there are 2 equilibrium pathways, and when the structure buckles, it switches from one path to another. Those 2 paths mean there are 2 solutions to the equation. In snapping, we just went through the problem. There was only one curve. It just so happens that parts of that curve are unstable. I use an analogy in the review paper you had to read of like, buckling is kind of like you're hiking in the woods and you come to a fork in the road, and you can either kind of climb up the mountain directly in between the fork, or you could take one path to the left and one path to the right. The paths to the left and to the right would be easier, and the path up the mountain would be tricky. So you kind of are on one path and you intersect with another path, and it's up to you to decide what to do. Snapping is kind of like you're walking along a path and there's a hole in front of you. And the only thing you can do to get beyond that path is to jump over that hole. There's only one path. Parts of it are stable, parts of it are unstable. And those are kind of the qualitative differences between these instabilities. And the last thing is, can you mathematically, now that you have a total potential energy, identify when parts of these solutions are stable or unstable? So again, checking your second derivative of your total potential energy. When it's positive, that's stable. When it's negative, it's unstable. When it's 0, that's when it switches. That's the critical point. So just one homework assignment. I suspect your life will be easier if you do this in Mathematica. You're welcome to build off of my Mathematica notebook. The one I showed you at the beginning of class is on the website, so you should be able to download that. And we can make this due again next Wednesday, so that way we have time to chat about it Tuesday in office hours and Wednesday morning in the office hours on Wednesday morning as well. Questions about all of this, either the homework or these questions of stability and equilibrium? Nothing? Oh. So your total potential energy tells you how much energy you're storing in your structure when you load it. The first derivative of that, and setting that first derivative equal to 0, tells you the equilibrium solutions to your problem. What configurations or what deformations of your structure are in equilibrium. Your second derivative of that tells you whether or not those equilibrium paths are stable or not. It's kind of like the pendulum problem. This is a stable pendulum path, but we know that, this is an equilibrium pendulum path, but we know it's not stable. Any perturbation, any little change here will cause it to go to its more stable configuration. We picked two really simple problems to look at. This is the problem of a hinged cantilever. Had 1 degree of freedom, that one spring at its base. And the truss, which because of its symmetry, had 1 degree of freedom, which was just the angular rotation of that truss. Real structures are continuous, which means that for all practical purposes, they have an infinite number of degrees of freedom. If I'm looking at a sheet of paper here and trying to evaluate kind of the shapes that it's going under as I'm doing very simple things with my hands here, you can start to see how there's curvature along this structure. That curvature might be varying locally. It might be really high over here and really low over here. This presents a problem for us. And the problem it presents is that the tools we use and we use just there to solve those kind of simpler problems, those mathematical tools are not enough to handle structures and solid materials. And I'll illustrate that now with a problem that on its face seems like it has nothing to do with structural mechanics. but it allows us to learn some of the mathematics we're going to need to handle this. And it's a problem that's a little bit even more general than what we're used to in structural mechanics, and it has to do with the principle of least action. We're familiar, I think you've probably heard the terms of principle of minimal potential energy, principle of virtual work. Kind of even more general than that is what's known as the principle of least action, which in words, what the principle of least action is saying is that, for instance, if I'm going to take a ball and throw it from here to there, what's the path that that ball is going to take? And it turns out the path that ball is going to take is if you can write down at every point along the ball's trajectory the ball's kinetic energy, and you take away the ball's potential energy, and you integrate the difference between kinetic and potential energy. You integrate that difference over time from when I throw it to when it lands. The path that ball will take will be the path that has the lowest value of that integral. Let me draw what I mean. I'm going to take a ball. I'm going to take a ball and I'm going to throw it from here to there. And I'm asking you what path that ball is going to take. You could do it, and the actual path will probably, I don't know, look something like this. And how do we find what that path is going to be? Well, I'm going to repeat what I just said. Imagine that you had the ability to calculate the kinetic energy and potential energy for all possible infinite number of paths between here and there. So if that's the actual path, we can imagine calculating that there could be a path like this, or a path like each of these paths. We could calculate the kinetic energy of the ball, potential energy of the ball. And if we integrate the difference between those two things from here to there, the path that it actually takes, that orange path there, is going to be the path that has the lowest value of that integral. So you have an infinite number of integrals of all these different pathways. An integral, if you integrate over an energy, you're going to get a scalar. You're going to get a number out, like literally a number. The path that it takes is the smallest number. So how do we use that to our advantage here? We can't obviously calculate an infinite number of different trajectories and then figure out what's going to actually be the action that is the smallest value. So we need some sort of a mathematical trick to do that. So what we can do is we can kind of formalize this a little bit and say, I'm going to have the height of the ball be the thing that I care about. And instead of throwing it from here to there, I'm going to throw it just up in the sky and let it come down. And I'm going to watch this ball as I throw it up in the air. I'm going to start at T1. And it'll land back down in my hand at T2. Throw it up, catch it. And the ball is going to do something. It's going to start at some initial position, some height off the ground maybe. I throw it up, it's going to go to some maximum height, and it's going to come back down. Maybe I'll catch it at some other height. I don't know, maybe it'll look like this for fun. And the orange path is the one that we expect the ball to take. We'll call this orange path x bar, which is going to be x bar of t. So I said we're interested, this is what's referred to as the principle of least action. We're familiar with the idea of principle of minimum potential energy. We've been using the principle of minimum potential energy. That's how we found the equilibrium configurations of the hinged cantilever and the truss. We calculated the energy, we minimized it, minimum potential energy. What's action? Because this is the principle of least action. Well, the principle of least action, your action, we'll denote this action with a quantity S. Your action is what I was describing to you in words. It's the integral from T1 to T2 of the difference between kinetic and potential energy. T So that's your action. Let me label these things for you. Kinetic energy, your V, of course, is your potential energy. You can probably quickly see how this starts to get, how I said this is a more general form of the principle of minimum potential energy, because if there's no kinetic energy, then that T goes away. And if you don't care about, if something's not varying in time, there's no inertial effects, no time dependence, you're static equilibrium, then you don't really have to deal with integrating over time, because who cares? It's just going to have no dependence on time anyway. So really all you need to do is minimize this quantity. And that's what we've been doing. But in general, structures are going to satisfy a problem that has to minimize both kinetic and potential energy. And we've written it down here in this, what's referred to as an action. The important thing I want you to take away is that if you do this integral, you get a number. There's an infinite number of numbers corresponding to the infinite number of paths that I could draw between those two spots. And the path that it actually takes will be the smallest number, the smallest action. S is your action. We can do a bit better because we know that if we're just handling like a ball that we're throwing up in the air, then we can write down the kinetic energy as 1/2 m mass times acceleration, but acceleration here is going to be, sorry, not mass times acceleration, mass times velocity squared. Oops, I don't have any room. Let me move that. There we go. We can also do the same thing for our potential energy and do something with like an mg times the height of the ball. I'm going to leave it as a potential. I'm just going to leave it as v of x bar for now. And you'll see why at the end of this derivation. So I can take this thing, and with that, So for every single path, we could calculate the action. And our mathematical problem is to find out whichever action is the smallest. This sounds familiar. This sounds exactly like what we've been doing. This sounds exactly like the type of stuff you've been doing in calculus, in which you have a curve, and you want to extremize that curve by taking the derivative of that curve and setting it equal to 0. The problem is, and you can kind of start to see this problem if you think about what you're doing for just briefly. If I was to give you like f of x as a function of x, and I'll plot some arbitrary curve. Maybe it looks like that. And I was to ask you to extremize this curve to find the minimum or the maximum. What you would do is you would take the derivative of my function f of x with respect to x, set that equal to 0, and what you would find are 2 points. You would find that you would get this point and this point. One's a maximum, one's a minimum. To find out which one's a maximum and minimum, you can take the second derivative and see the sign of that derivative. Here's the problem. For an ordinary function, f of x, to minimize or maximize that function, you take the derivative, you set it equal to 0, you get a point. You get one value, you get a number. X is equal to whatever this value is. But if you go back to our problem, we're not looking for a point. We're looking for a curve. We're trying to take the derivative of some function, say S, our action, and we want to minimize or maximize that function, but the result of that is not going to be a point. We need that to be a curve. If we were doing this for my sheet of paper, what I would be doing is I would be trying to minimize the action of this object, and the result wouldn't be a point, and it wouldn't be a curve, but it would be a surface or a manifold. You're solving for something that is going to give you a function that tells you exactly where every point of this paper is in space. If I was to do this for a blob of jelly or your body or the chairs that we're sitting on, that's a 3D object. I'm looking for not a point, I'm looking for the 3D shape of that object that minimizes this action. If I want to say this problem more mathematically, what I would say is ordinary calculus Ordinary calculus gives us the tools to minimize a function of a variable. But our action over here S bar is a function of the kinetic energy, which is a function of position. And it's a function of our potential energy, which is a function of position. Our action is not a function of a variable. Our action is a function of a variable. That sounds really confusing, This actually has a very special term for it. This is what's referred to as a functional. Ordinary calculus fails us when we want to minimize a functional, because the result of minimizing a functional is not a point. It's either a curve or a surface or a 3D shape. So we need something else. We need another tool to help us. The tool we need to minimize functionals is what's referred to as either variational calculus or the calculus of variations. The nice thing is that we can kind of follow some of the blueprints from ordinary calculus to do this. What we're trying to find is a minimum or a maximum. And these ideas of minimum and maximums are still the same. If we can, I keep harping on this because if you can minimize your total potential energy, you can find the shape that your structure is going to deform it to. And if you can check the second derivative of that total potential energy, you can determine if that structure is stable. The challenge is for continuous structures, actually minimizing it is really a pain. You need an entirely new set of mathematical tools, but the ideas are the same. The idea is that if I'm at a minimum, then to first order, which means to a kind of a small, remember the ball on the hill. If I'm at a minimum, then a small perturbation of that ball on the hill will be stable. Will return back to its place. So if I was to take a configuration that I thought was stable, what I could do would be to add a little change or a little variation in that curve and check if that is actually stable. And that's really what variational calculus does. It says, take your function that you're trying to solve for, add a little function to it that's slightly different, and then check to see if you found check to see if the configuration you found is actually the one with the lowest action. So visually, it looks like this. So this is our curve. What I want to do is say, let's look at a different curve. We'll call it x of t instead of x bar of t. It's going to be slightly different than our orange curve. I'm going to exaggerate that difference right now for the sake of drawing it, but I want you to imagine that it's really a tiny variation of our actual curve. And it looks like that. You'll notice that I started this purple curve and ended this purple curve at the same spots. That's really important. Kind of would be weird if you're saying, I'm going to solve for a trajectory of me throwing a ball up in the air. And the solution I found is that I was actually standing over here underground. Like it has to have some initial, in this case, initial conditions that match. This becomes a much bigger and more important problem in structural mechanics because in reality, we're not handling initial value problems. We're handling boundary value problems. Boundary value problems are really hard. But boundary value problems are really important because I want to say, what's the shape of this sheet of paper? The shape of this sheet of paper is absolutely determined by my boundary conditions that I'm applying to it here. So I need to know something about the paper in space, but I really also need to know what's happening at these boundaries and how these boundaries might be changing as I'm deforming it. Boundary value problems are a lot more complicated than initial value problems. It's kind of like initial value problems are, you have to shoot an arrow up into space at some initial angle and figure out where it's going to go. A boundary value problem is you have to shoot an arrow at some angle, and it has to land at some angle at another spot, some exact distance, some far away. Firing an arrow is, you can do this a million different ways and just kind of follow where it goes. But firing an arrow so that it actually lands where you want it to at the right angle is a lot more complicated. Mathematically, that plays out as a severe restriction for us, which is why there's so many computational tools for solving these problems. Okay, this is our fake curve, the purple one. It's called x of t. And at every point in time, there's a slight variation between x of t and x bar of t. So I could imagine drawing like a little there's a difference here. At every point in time, there's some difference between these two curves. That difference is a variation. There's a variation between these two curves. We'll call that eta of t. And so we can write this out more mathematically, and we can say that, well, I have a new function, x of t, which is just some arbitrary function. It's just, we just made it up. And we know that x of t should be equal to the true function, which we don't know. That's what we want to find, plus some variation. And you can already start to see the problem here. That variation we're adding, it's time dependent. It's also a function, right? Like I could have any arbitrary, eta could be whatever the heck we want it to be as a function of time. And so if eta can be that, then therefore x can be some crazy variation as well. This starts to highlight why the mathematical tools are different than what we're used to in ordinary calculus. But nonetheless, we just insert this into our action. And so our action for S, which would be the action of our purple curve. I'll write it in purple. The action for our purple curve is equal to the integral from t1 to t2. You can't see that, that's a t, it looks terrible. t1, t2 of mass over 2. And now I have to handle derivatives of x bar of t plus derivatives of my new function eta of t. And my total potential energy, we're just going to say it's now a function of x bar plus eta. Let me just remind you of what we've done here. X bar is the solution to our problem. It's the actual trajectory that we want to find. We don't know it, but that's what we're trying to find is x bar. It's the actual path this takes. If it's a beam it's the actual curve of my beam. If it's a plate, it's going to be a function of x and y, and it's the actual shape of my plate, which I don't know. To find it, what we do is we say, I'm going to take my unknown, the thing I'm trying to find, my orange x bar of t, and I'm going to add to it some arbitrary variation, eta of t. We don't have to specify eta of t because it's arbitrary. It could literally be anything. That statement I'm making right there is actually like the most important thing, is that eta is arbitrary. It can't be 0. If it's 0, then we actually haven't changed our problem at all. We just have an unknown and there's nothing's different. So eta is something, it's not 0, it's some arbitrary function we're going to add to the real answer. Once you understand that, then it's just a little bit of turning the crank. We insert x into our action. So instead of x bar, we have now an x bar plus my variation. Instead of a total potential energy, just depending on the true total potential energy, it's going to be some perturbed total potential energy. It's going to be the potential energy that's actually happening. Plus we varied it just a little bit in some arbitrary way by adding eta to it. I said something in my definition about minimums and maximums that, you know, a minimum should be, a minimum's value shouldn't change to kind of small, like to a small perturbation or a first order change variation. What does that mean, first order? That's the word that I'm kind of harping on here. Well, we can see what that means, this concept of first order and second order, which is going to be really crucial to us. Like the difference is not semantic. You're going to see that we're going to map first order to first variation to equilibrium, like we did with first derivatives. And second order will be what we think of as second variations or second derivatives, which will tell us stability. So we need to know what we mean by first and second order. It's not that hard. I take this thing, I'm going to say I know how to expand this. It should be equal to dx bar dt squared plus 2 times dx bar dt d eta dt plus d, oh gosh, that eta is awful, plus d eta dt squared. This, since it only contains first derivatives in eta, is first order in eta. And this, as it contains second derivatives, oh gosh. That's a terrible color. Is second order in eta. To establish a minimum, we only need to consider the first order changes in eta. It's just like saying to find equilibrium, we just need to consider the first derivatives of our total potential energy. That gives us forces, first order variations in our total potential energy, gives us forces, it gives us things that will allow us to establish equilibrium. What do we do with this thing over here? And the answer is, we know that our variation is arbitrary and we know that it's small, right? We said, let's just pick some small change. We're trying to find something that's a minimum. Whenever you have something that is kind of perturbing a function, or like you're adding something to a function that you know is small, or just in general, like mathematical engineer toolbox that you should have at the ready. Anytime you have an equation, especially an equation that's hard to solve, and you can identify something in that equation that is small, then what you should do is do a Taylor series expansion about that parameter being small. That's probably something you haven't done since Calc 3 in Mathematica. It's really easy to do. You just type in series, your thing that you want to do, and then tell it what parameter and to what order. It's remarkably easy. I'll show you at some point. But we'll do it out by hand here for a second just to remind you. So your Taylor series of this thing, why are we doing this? We're doing this because we want to collect the first order term. So we've got the first order of the kinetic energy is this term. And we want to figure out what the first order of this term is. So what we're going to do is we're going to do a Taylor series expansion by the fact that eta is small. This will probably maybe be familiar to you as I start. If you do a Taylor series expansion, the first order term should be the term in which eta is exactly 0. So it's just going to be v of x bar. And then we add to that the first derivative of v times eta. Remember, it's like 1 over n factorial times the first derivative times the thing. 2 plus 2, 1 over 2 factorial times the second derivative times the thing squared. Keep going, keep going. It gets more complicated if you're not doing it about 0, but we're doing it about 0, so ours is not that bad. So remember, this is like 1 over 1 factorial, that's 1. I'll write the eta first. The prime of eta bar. And then we can do 1 over 2 factorial, so it's 1 over 2 factorial is 2 times eta squared times my second derivative of x bar. And we could keep going if we want. First order means the term that we're interested in, eta, is appearing kind of the first power. So again, here's our first order term. Here's our second order term. And so now we can take our energy. Sorry, we can take our action. We can say that we can write our action out like this. M over 2 times this quantity. That's the kind of 0th order in eta, right? Because eta doesn't appear at all. So the 0th order terms in eta are the ones I'm highlighting here. No eta, no eta. So it's 0th order in eta, looks like this. Then the first order in eta, the 2 and the 1/2 cancel out, so that goes away, and we're left with just mass times dx bar dt, d eta dt. And that's my yellow term, so let me highlight that in yellow. This is my yellow term, and then we have to subtract off of that the potential energy, which is going to be eta minus Vx bar beta. Again, that's my first order term. I should highlight this for. And then we can write, and this is what they would do mathematically. It allows you to kind of take any term that is higher than second order or higher and just lump it all into one and say, well, we have some other terms that are all big O, squiggly O, order epsilon squared. So this is a big O. And it basically means we're going to add to that terms of eta squared and higher order terms. Sometimes you might see this written as like you'll often hear people describing like discarding higher order terms. And that's what they're saying. And for this particular thing that we're interested in, which is finding the equilibrium configuration of a structure, finding what's analogous to the first derivative of the total potential energy, we only need first order terms. So we don't need this term in gray. We can just discard it for now. It's important later, but we don't need it for right now. Okay. Let's take a break. And if you have questions during the break, let me know. We'll take a break till like 10:02.
All right. So you put both top and the bottom like together, like expand it out for the equation, right? Like you have like circle like the two blues.
Yeah. So what I did is I should be more clear here. So what I did is let me change my notation here. What I did is this is the kinetic energy. I expanded the kinetic energy so that I isolated 0th order and epsilon. So this thing has no epsilon terms appearing. First order in epsilon, so epsilon appears, but not with a power. Second order in epsilon. Epsilon's kind of, you can see a squared there. I did the same thing for the potential energy. I said we have 0th order in epsilon, first order in epsilon, second order in epsilon. So we kind of expanded all of them so that way we could, what we want to be able to do is look at the action at 0th order, first order, second order, so on and so forth. And so that's what I did there is I basically just split this thing up and then I rewrote them in a different order. So I grabbed the 0th and 0th, first and first, and then second and second. All right. Did any questions come up during the break? For some unknown reason, our universe says that things should tend to minimize their action. Their action is the integral of their kinetic energy minus their potential energy over time. Whichever action is the smallest corresponds to the trajectory you'll see, the deformation you'll see. So the question is, how do we minimize an action? Minimizing an action is different than minimizing a function, because an action is a function of a variable. We're used to figuring out how to minimize a function of a variable. But now we have to handle this other thing, a functional, which is a function of a variable. And minimizing that is tricky because we're not looking for a point, we're looking for curves and surfaces and volumes. So what do? You do something similar to what you do in ordinary calculus, which is kind of like you find the point you're at, you add a slight variation to it, you take the limit as that goes to 0, and you get, for the fundamental theorem of calculus, how you calculate derivative. We're doing something similar here. It's just that in that, what you're doing is you're finding a point x, you're adding another point delta x to it, which is like a literal change in your independent variable. Here, we're not able to do that. What we're doing is we're taking our function, x of t, and we're adding kind of a slight variation to that function, eta of t. And what we're going to do is we're going to use that to allow us to minimize our system. I haven't shown you that yet. But that's what we're doing, is we're taking a function and we're just adding another function to it. This is really common in various things of Fourier analysis, where you say, like, I can just approximate this by stacking together like sines and cosines to solve problems. So we're going to actually do that too. Not today, but we're going to do something like that as well. But what you're doing, you're saying, well, my solution is probably some combination of functions if you just add one and then add smaller ones to smaller amounts to them. It's the same idea. So if that's familiar to you, great. If not, no big deal. So here is the action for the actual minimum action. This is the action that is the smallest. It is the true trajectory. We don't know it because we don't know x bar, but we do know that this action is the one that is the minimum, because it's the action corresponding to the true trajectory. We just made it up, but we know there has to be one. So this action is the action that we would expect to see in this problem for our ball being thrown up in the air. This action is a variation on that first one. And we found this action by taking the true path and adding a small thing to it. And I wrote it in a different way. I wrote, instead of as like kinetic minus potential, I wrote 0th order kinetic minus 0th order potential, 1st order kinetic minus 1st order potential, 2nd order. The reason I wrote it this way is because, look, the first term I circled in blue here is this term. They're the same. So at 0th order and epsilon, this is exactly the action of the true path of the ball. So what does that mean? It means that if I take the action that I'm interested in and I subtract the true action, then the difference between this and this will be 0 if my function x bar is the true trajectory of my ball. Let me show you it mathematically, because I think in that case it might be easier to make sense of. I can say that S minus S bar should be 0 the difference between S and S bar will be 0 if my function x bar of t is the function that minimizes the action. It's kind of mathematically obvious, right? If these two things is 0, then all the other terms don't matter. We've found the solution. This quantity here, the difference between the action of my perturbed state, where I've perturbed my true solution by adding a small thing to it, or my variational state, where I've varied my true thing by adding a small quantity to it. This quantity here is what's known as the first variation in your action. These symbols look the same, so let me be clear what I'm talking about here. This is a delta, and it refers to the variation in your quantity. So it means I've taken my quantity and I've added a small perturbation to it. And if you see delta written, that's your first variation. If you see delta squared written, that's your second variation. Delta cubed, your third variation, so on and so forth. Your first variation is analogous to the first derivative that we've been using to find equilibrium. If I set my first variation equal to 0, that's analogous to setting my first derivative of my potential energy equal to 0. That will allow us to find equilibrium. If I take the second variation and check the sign of it, that will allow us to check stability. It's a first variation because we've only considered first order terms here. Good so far? Okay. Okay, so that means the difference between this, which is this thing, and this thing, all that's left, the actual difference between here and here, is just my yellow stuff, right? So this is my first variation in S. This stuff is my second variation in S, and higher order terms. Does everybody see that? So now the challenge we have, the mathematical problem that we have to handle is, what on earth do I do with this first variation? So let's write it out. So let me go over here. The first variation in S is equal to the integral. That's terrible T. Between T1 and T2 of my mass times dx bar dt times d eta dt minus eta times v x bar. So let's think about what this is telling us. First off, I want to remind you, as I keep reminding you, that we don't know x bar. It's the solution. It's what we're trying to find. We want to find, if we can find x bar, then we've satisfied our problem. No matter what value of eta we choose, remember, eta is arbitrary. The only rule about eta is that it can't be 0. Because if it's 0, then you actually haven't varied anything. Eta is arbitrary, though. It could be any number. However, we know that this thing, oops, you can't see me. We know that in order for x bar to be a minimum, this integral has to be exactly equal to 0, right? We established that with this remark here. So in order for x bar to be a minimum, this integral has to be exactly equal to 0. If eta can't be 0, the only way this integral can be 0 is if what multiplies eta is 0. Right? It's like if you have a times b equals 0 and a is not 0, then b has to be 0. In this case, a is eta, can't be 0. Multiplying b is the junk in here. That product has to be 0. That only can happen if the thing multiplying eta is 0. It's almost like, it almost sounds simple, but there's one little thing that presents a challenge for us. And that is, this term's fine. This term has eta appearing in it, and we know that whatever multiplies eta has to be 0. But this term does not have eta. This term has a derivative of eta. And that actually presents a problem for us because we know that eta has to be 0. Sorry, we know that eta cannot be 0. It's arbitrary. But we actually don't know anything about the derivatives of eta. We have no rules about that. So we have to figure out how to get rid of this term that I put in a box because we don't know any constraints on that derivative of eta with respect to time. So we want to get rid of, and the thing that you should keep in mind, the thing you should take away from this is if you're ever doing anything with variational calculus, you always end up kind of perturbing some function, and you end up with some big energy or action in which you have your perturbation parameter, eta here, appearing, and derivatives of eta. And the thing that I want you to remember is if you see derivatives of eta, you have to get rid of them. How do you get rid of them? Well, you get rid of them by using an old friend from calculus, which is integration by parts. Right? Because what we have here is the integral of u dv. Okay, what's what here? This is my u. Oh, that's terrible. And the box thing is my dv. And remember, if I take the integral of u dv, I can set that equal to u times v minus the integral of v du. Right? This is integration by parts. If this is, let's see here, if this is u, and this is dv, and remember this is all tucked inside of an integral, then the integral of u dv is equal to uv minus v minus the integral of v du. I think technically the dt should be in there in my definitions, but for our purposes, I'll show you how explicitly this works. Okay. So let me just check my notation. What did I call F? Let's not do that. All right, so now we have to integrate by parts. So variational calculus, this is like this is the turn the crank part. You write everything down, you input a variation, and then it's integration by parts. If you have second derivatives of eta, it's integration by parts again. The beam equation involves fourth order derivatives, which means you integrate by parts 4 times. It's not that bad. It's really kind of like you get used to the machinery of it. So let's see here. So what I want to do is let's put this back in terms of stuff that we care about. I'm saying that I have the integral of m dx bar dt times d eta dt times dt. Now that should be equal uv. So what's u? U is, again, u hasn't changed. So it's m dx bar dt times eta. Now remember, this is tucked inside of a definite integral. So this is actually not just uv, it's actually uv evaluated at, t1 and t2. This term, not in this problem is kind of boring and simple, but for most problems in structural mechanics, this term is really important because these are conditions at, in this case, your initial conditions. But as I mentioned, in structural mechanics, you're typically dealing with boundary value problems. So where these are evaluated at are locations. So what you end up with when you do variational calculus on a structure is you not only find the equations of equilibrium, but you also find the boundary conditions. Now, as folks who are kind of just being introduced to structural mechanics, you're almost always provided the boundary conditions. It gets simply supported, or it's clamped on one end and free on the other. There are lots of problems that finding the boundary conditions is not really trivial. In the case of this, the boundary conditions on a free plate are not easy to just internalize in terms of what conditions are we requiring kind of along my edge here. So when you do variational calculus, you get the boundary conditions for free. They just drop right out of integration by parts. So it's kind of a nice bonus. And I'll give you a problem to practice where you can kind of see that explicitly happen, but after you finish this next homework. Okay, so that's the first term, but then we need the integral of v du. So we have to subtract off the integral from t1 to t2. I lost that over here. I'll put it back. t1, t2 of eta times d by dt of all of this stuff. And we'll deal with that in a second. But here's what I want to show you. What we just did is we took this term over here that is annoying, and it's annoying because we don't know anything about d eta by dt. And we got rid of d eta by dt by integrating by parts. Because now look, I took this integral and I replaced it with something that occurs at the boundary. So it's outside the integral, so we don't have to worry about it right now. And this term that's in the integral gets replaced with this term. And look, this second term only has eta in it. This is great because we know eta can't be 0. We know that eta times this other stuff has to equal 0. So now we can just simply collect our terms. So let's do a little bit of work here. So let's go back over to here. Write down our first variation in S is going to equal m times dx bar dt times eta of t evaluated at t1 and t2. I don't have enough room, so let me move that down. Okay, that's the first term. It's a boundary term. We don't have to care about that for right now. I have an integral from t1 to t2. This thing times eta of t integrated over time. And I have this thing, which is the integral from t1 to t2 of v prime times eta of t dt. So now the key thing, and I keep harping on this because it's really important, is that eta only appears in the integrals without derivatives. It's just eta by itself. Eta, eta. In this particular problem, what's eta at t1? Oops. And eta at t2. Remember, eta is the difference between the orange and the purple curves at a point in time t. Yeah, it's exactly 0. It's 0. So this whole term goes away. Great. And now, since we're going to go back to this idea that eta is arbitrary and not 0, and it's multiplying some stuff, a times b equals 0, a is not 0, so why don't we collect things inside of our integral? So we can say t1 to t2, negative mass times second derivative. If we say our mass is not varying in time, we can just distribute that derivative into x. So all I'm doing is putting all this stuff back in the integral together and factoring out eta. Here's the a times b equals 0. Eta can't be 0. Eta is arbitrary and non-zero, which means that for this quantity to equal 0, if this term can't be 0, then this term must be 0 for x bar to solve our problem. And so all we have to do is kind of pull out this term. And my last question is, what's the derivative of a potential with respect to x? We did this all last week. If you have total potential energy, you take the derivative, you get a if my energy has units force times distance, and I take my derivative of my energy with respect to distance, I get a force. So we just found through energy methods that F equals ma. What you get as a result of variational calculus is the governing differential equation you need to solve to find your problem. So this doesn't look like a differential equation when you write it as F equals ma, but it certainly looks like a differential equation when you write it this way, and you have a second derivative, second order ODE, and we found Newton's second law from starting from an entirely different place. We started from energy. We started from the idea that for some reason in the universe, everything tends to minimize its action, and if you minimize its action, then you arrive at the equations you need to solve your problem. So the result of this is not, we didn't get X bar, but we got the equations we need to get to solve for X bar. And we got it a totally different way. The energy methods and the force methods are identical. There are certain problems that it's easier to use one versus the other. But now we're in a position where we can not only find equilibrium, we can go back and say, if we know we're at an equilibrium condition, then we can go back to our action up here. This minus this has to equal our first variation. If our first variation is equal to 0, then we can just only focus on our second variation. And just like we did before, the second variation is analogous to the second derivatives of our total potential energy, which allows us to check for stability. Because remember, I wrote this up here, we don't know if we've solved for a minimum or a maximum. We can only determine if we've solved for a minimum or a maximum, or a stable or an unstable equilibrium, by checking the second variation. For a problem like this, where you throw a ball up in the air, yeah, it's going to be, you're going to find that it's stable, it's positive always. For a problem like your structures in which you're pushing on them, you're not going to find that to be the case. So I just spent an hour and a half of your time deriving F equals ma, which is either amusing or you might be resentful of me. But this is the way you minimize, this is the way you find the equations you need to solve to determine the shape of a deformed structure. We did it for a really simple problem. Now that we have the tools, we can start to show you how this works for some more structural related problems. So what questions do you have for me?
I got like a little confused towards the end, like again, you know, like the box is 0, right? So then like, does that integral become F equals ma, or like what's inside, left inside of this? Yeah, so the idea is, that's a great question. So if you couldn't hear at home, the question was like, okay, the box has to be 0. Does the integral become F equals ma, or does the what's remaining?
Does what's remaining? And I would say, think of it this way. That integral has to be 0. The only way for that integral to be 0 is if the terms inside the purple box are 0. Because then you're integrating 0 times something that's not 0, and you're assured that you're getting 0. So the integral, essentially, it's not that the integral doesn't matter, it's that the integral, we don't need it for the moment. We can just find the equations we want to solve, and they have to be equal to 0.
So we can ignore like the orange part on the last.
Yeah, so it's not exactly. So the idea here is that this is kind of like A times B equals 0, where A is not equal to 0. That's all we're doing. We added an arbitrary perturbation to our structure. We said, we don't know what the shape is, but we do know that if we just perturb the shape a little bit by some amount, we can use these rules, these simple ideas of a times b equals 0 to help us find the shape that actually does minimize the action. So eta is arbitrary. You can add, it's almost often unspecified. You just say, I'm going to add a small thing to it. It's arbitrary. And the key thing is that it's just not 0. And then you're saying, well, okay, I've got this thing that's not equal to 0, but this quantity has to be 0 because this makes sense, right? You can kind of see it mathematically. If the action is kinetic minus potential, and then I perturb it by adding a slight variation, and I stick this thing into my kinetic and my potential, and I get this kind of complicated mess down here that depends on the true answer and then perturbations on that thing. I say perturbation, I keep using that term, but it's kind of it's a way of saying, like, take your function and poke it a little bit. And we're poking it by adding an eta to it. So what we did is we added this arbitrary perturbation to it, and then by just rearranging some terms, we saw, oh, what you recover is the actual action for the path that we want to find, plus some other things. And so if I take my action of my perturbed system and I subtract off my action of the true system, the only way on an equilibrium is if the difference between this and this equals 0. And that's the reason why you have this a times b equals 0 thing emerging, is because, look, this is this. And so the difference between this and this must be 0. And that difference to first order is this. First order tells us if we're in equilibrium. Second order tells us if we're stable. I know this doesn't seem connected to structures yet. I tried to pick the simplest possible way to introduce this, but it's really at the heart of structural mechanics. And it's at the heart in two different ways. One way is if you're trying to analytically predict something, like pen and paper, try to find the equilibrium configuration or the buckling pathway. You can do this. But second is that everything here is written in terms of integrals. Integrals are great for computers. And I'm going to say this again a couple different times, but this exact approach that we just used right here is how you derive the equations that you're asking your finite element solver to solve. And the reason is, look at this. The equation we found down here is the equation we actually want to solve. It's a differential equation. It requires that at every point in time, my second derivative of my thing is exactly equal to 0. Computers are terrible at that. Numerical precision, numerical error enters into the equation, and requiring high order derivatives to be exactly equal for all points in time is really challenging. So instead, if we look at what we have here, all we're saying is that over some domain, T1 to T2, I just need the average to be 0. So any of those numerical fluctuations are fine as long as the average between them is 0. So computers, it's far easier to solve integral equations in which you're averaging and saying, like, over some domain, I just need the average of this quantity to be 0. That is a much more sound way for computers to determine the deformation of an object than requiring it to be 0 exactly everywhere. You'll hear me say this again, I'll repeat this, but the derivative equation here, people refer to this as the strong form. It's a strong in the sense that it has to be satisfied at every single point in time in your discretized structure, or every single point in space if you're dealing with a static equilibrium. At every single point in space, I need multiple derivatives of this thing to be equal to 0. This right here is what's referred to as the weak form, which just says, I just need it on average to be 0 in between my, say, if you have a mesh, like in between my mesh nodes or something in my structure. So we use this exact same math to derive the weak form, which is this. And then your computer is solving that weak form to tell you what the structural deformation is going to be. So this math is useful for you kind of doing stuff on pen and paper, but it's also the bedrock of how your computer is solving these structural mechanics problems, because integral forms are easier for computers than derivative forms. I'll probably repeat all this, and so, but I'm just kind of using it to help motivate now as well. All right.
You won't be using this for the homework, right?
You don't need this for this current homework. You can just do ordinary derivatives. But I will try to assign another homework where you can practice some of this. Mm-hmm. It'll probably be like next Tuesday, so you can kind of, and I know they'll overlap briefly, but it'll just so you can practice some of this, because I recognize that it's new math. I'll make them easy too, just so you can get some experience with it. But yeah, you won't need this for the current homework. You should be able to do the stuff we did. My Mathematica notebook that's on the website should be helpful for the current homework. If there's no other questions, have a nice weekend. And yeah, we'll talk again soon. Thanks, everyone.